In this video, we're going to talk about limits and continuity of vector functions. And so these are going to be direct analogs of limits and continuity of real valued functions that you see towards the beginning of a Calculus 1 course, just extended to the concept of a vector function. And so for a limit, we're going to give kind of a vague definition of limit, kind of an intuitive definition. And so what I need here is I need a vector function r of t with component functions f of t, g of t, and h of t. And I need a vector L with components L1, L2, and L3. So we have a vector function, and we have a vector L with fixed components. So in this case, we're going to say L is the limit of the function r of t as t approaches a written in sort of the normal limit way, using the normal limit notation. So limit as t goes to a of the vector function r of t equals the vector L. The only difference there is that we have arrows over r and L. If we can make r of t as close as we want to L by taking t arbitrarily close to a. Right, now this is kind of a vague definition, and particularly we're talking about as close as we want and arbitrarily close to those phrases. And there are ways to mathematically define those phrases using epsilon and deltas. And some of you might have seen an epsilon delta definition of a limit in Calculus 1. You can do the exact same definition here and it makes complete sense. But we're going to skip over that rigorous definition simply because we're not going to need it. We're going to do very little with limits, but we do need to cover them so that we can define derivatives and integrals. And then once we have those concepts, then we're not going to have to come back and compute limits too often. And so the definition of the rigorous definition of a limit will not be needed. Right? However, we do need some techniques to help compute limits when we have to. And so we can pretty quickly come up with a really natural way of computing a limit of a vector function, and sort of probably the way that you would hope would work actually will work. And so if we think about what it means here for the limit as t approaches a of this vector function r of t is equal to L, this was what we just defined. This limit approaching, the limit of r of t as t approaches a is L. Well, if I put in the components, if I put these vectors in component form, this is saying the limit as t approaches a of the vector f of t, g of t, and h of t has to equal the vector L1, L2, and L3. Now thinking about this logically, the only way that this vector function f of t, g of t, h of t can get close to the point L1, L2, L3 is if each of the three components of this function, f, g, and h, get arbitrarily close to L1, L2, and L3 respectively. Right? There's no way that h of t does not approach L3. There's no way that g of t doesn't approach L2. And there's no way that f of t doesn't approach L1. And so what we can see here is that when we take this limit, what we're really doing is taking a Calc 1 limit in each component. Right, we want each of the three components to approach the particular value that we want. And we can obtain that by taking the limit in each component. Right? So now notice that these three limits, these are limits of scalar functions. So these are all limits from Calculus 1. So in order to compute a limit of a vector function, what we need to do is just take the limit of the three component functions, and this is a Calculus 1 problem. Right, so for example, let's say we had the vector function r of t given by components 2 minus sine t over t, negative 3 plus 3t squared, and the square root of 4 minus t. And we want to compute the limit as t approaches 0 of this function. Right, so this is the limit that we want to compute. Right? And so in order to do this, all we need to do is compute the limit as t approaches 0 of each of these component functions. So the limit is t approaches 0 of 2 minus sine t over t. The limit as t approaches 0 of negative 3 plus 3t squared. And the limit as t approaches 0 of the square root of 4 minus t. And now each of these three limits can be computed using techniques from Calculus 1. Right. Now the first one I'm going to actually do off to the side. It's probably the most difficult of these. So what we have here is the limit as t goes to infinity of 2 minus the limit as t goes to infinity of sine of t over t. All right, so I'm using a limit law here to break up the limit of a difference as the difference of the limits. Well, that first limit there, of course, is 2, because the limit of a constant is always that constant. And the second one, we actually have an indeterminate form. If I evaluate the function at 0, I get 0 over 0. And so we can use L'Hopital's rule, which says that this is equal to the limit as t goes to 0 of cosine t over 1. So we take the derivative of sine of t and t independently. And so when we evaluate that at t equals 0, cosine of 0 is 1. So this becomes 2 minus 1, which is just 1. So the limit, the first component of my limit here is 1. So I had to do a little bit of work off to the side for that one. The second component is a polynomial, so we can just evaluate it at 0. So that would be negative 3 plus 3 times 0, so negative 3. And the last one, we again just evaluate at 0, so we get the square root of 4, which is 2. So the only one that we had to do some work on was that first component. And this is very standard for these problems. Sometimes these limits are very easy to compute. We just plug in the value a, or in this case 0, to each of the components. But if we have to do some factoring or rationalizing the denominator or L'Hopital's rule or some other limit technique, sometimes that is required in certain components. Right? Now, one thing I want to point out about this particular function, we just found that the limit as t goes to 0 of r of t is this vector 1, negative 3, and 2. I want to point out that r of 0 is not defined. Right? I didn't give an interval where this vector function was defined, but certainly any interval that is going to exist where this function exists cannot include 0. And the reason is because of that first component. We have a term that divides by t. And so t is definitely not able to be 0 in this case. And so if we wanted to extend this vector function to include 0, the correct value to include would be this limit that we just found. Right? If we take values of t closer and closer to 0, this vector function is getting points closer and closer to 1, -3, and 2. So once we have limits defined for vector functions, we can easily define continuity. All right, so we're going to say that the vector function r of t is continuous at the value t equals a. So we're going to define continuity at a point first. And that's going to be defined to be the case if the limit as t approaches a of r of t is equal to r of a. And we're going to simultaneously say it's continuous on the domain D if it's continuous at each point in D. So this is exactly what you did in Calc 1. You defined continuity at a point first, and then continuity on an interval if the function were continuous at each point in that interval. And it's the same thing here. Now, one thing to kind of point out here, this defining feature of being continuous, that the limit equals the function value. Notice that this does actually say three things. This tells us that, first off, that the limit as t approaches a of r of t exists. It also tells us that the function value r of a exists, and that these two values are equal. So the example that we just looked at where we computed the limit as t went to 0, we saw that the limit of the vector function existed, but we also saw that the function value at t equals 0 did not exist. And so that is a function that is not continuous. Now, combining these few things that we know about limits and continuity, we can come up with a really quick way of determining when and where vector functions are continuous. All right, so let's say we have this vector function r of t with component functions f, g, and h. Which is continuous at some value, let's say at t equals a. Right? So if this is the case, then this means that the limit as t approaches a of r of t is equal to r of a. That's our definition of continuity. Now, if I use the component forms here, the limit as t approaches a of r of t is the same as the limit as t approaches a of f of t. The limit as t approaches a of g of t, and the limit as t approaches a of h of t. And r of a is the function f of a, g of a, h of a. And so the only way for these two vectors to be equal is for the corresponding components to be equal. Right? And so what we have here is we have to have limit as t approaches a of f of a, or of f of t rather, equal to f of a. We need to have the limit as t approaches a of g of t equal to g of a. And the limit as t approaches a of h of t equal to h of a. And so if all three of these things are true, if these three limits are all equal, then what this is saying is that f of t, g of t, and h of t are all continuous at t equals a. And so if I have a vector function and I want to determine if it's continuous at a point, or if I want to determine where it's continuous or not continuous, all we need to do is look at the component functions and determine when all three of them are continuous. Right, so for example, let's find all places, so let's determine all discontinuities for the vector function r of t defined as e to the t sine of t times I plus 2t over 3 natural log of the absolute value of t, j, plus x plus 1 over x squared minus 1 times k. Right, so I've given this vector in standard basis form, but we have the components e to the t sine t, 2t over 3 natural log of the absolute value of t, and x plus 1 over x squared minus 1. And so in order to determine where this is continuous or discontinuous, we simply need to analyze the continuity of the three component functions. Right, and so if I focus on the first component function, e to the t sine t, e to the t is continuous everywhere, sine of t is continuous everywhere, and the product of two continuous functions is continuous. So this particular function is continuous for all t. Okay? So that first function doesn't pose any problems whatsoever. So now we consider the second component, 2t over 3 natural log of absolute value of t. So this particular function does have some values where it's discontinuous. All right, so let's go through and look at what could go wrong. So the first thing, there's no problem with the 2t or with the 3, so we can sort of ignore those. So we only have to focus on the natural log part. The natural log is only defined for positive values, and so if t is positive, then natural log of absolute t is fine, and if t is negative, the natural log of absolute t is fine, since the absolute value of a negative number is a positive. However, we do have an issue when t is equal to 0. So the natural log of 0 is undefined, and so when t is equal to 0, we get an undefined denominator. Now, in addition to this, we also have a fraction here, which means we have to watch out to make sure the denominator is not equal to 0. And so natural log of t is equal to 0 when t is equal to 1. So we cannot have t equal to 1 in this case, because if we evaluated at 1, we would get 2 in the numerator, and we would get 0 in the denominator. And the same thing would happen because of the absolute value when t is negative 1. So we also have to throw out negative 1. So the second component is not continuous when t is 0, 1, or negative 1, which means that our overall vector function is not continuous at these 3 points either. Now we move on to the third component, x plus 1 over x squared minus 1. And so this factors in the denominator. So we have x plus 1 over x minus 1, x plus 1. And so we want to be careful here. We could, of course, go ahead and simplify this, but that would be ignoring the whole in the function. So this particular function is not continuous. We just look at this denominator when x is positive 1 or negative 1. In that case, we would get a 0 in the denominator. You might want to cancel the x plus 1s and then say it is actually defined at negative 1, but the actual function, the original function, is not. That would be a simplification at every point except for negative 1. We don't want to do that. So here we get this is not continuous at these 2 points. Right? And now we look, and if we look at all 3 of these components, we know as long as all 3 of these components are continuous, so will the original function r. And so the only points that we have discontinuities will be at t equals 0, -1, and +1. Right? At each of these 3 values, at least one of the component functions is discontinuous, but at all other values, all 3 are continuous, and therefore the only discontinuities for this function lie at 0, -1, and 1.